Blessed day, everyone. I am Julia Ann Polias Magpusaw, and I am assigned to discuss with you the CPU scheduling. The chapter objectives. First is to introduce the CPU scheduling, which is the basis for multi-program operating system. Second, to describe various CPU scheduling algorithms. Third, to discuss evaluation criteria for selecting a CPU scheduling algorithm for a particular system. And the last is to examine the scheduling algorithm for several operating systems. CPU scheduling is the basis of multi-program operating system by switching the CPU among processes. The operating system can make the computer more productive. It also describes as a process of determining which process will own the CPU for execution. The main task of CPU scheduling is to make sure that whenever the CPU remains idle, so when we say idle, the CPU has nothing to do with the program or has nothing to do, and there's no program to be executed, and there's no processes that are available to be executed. So the main purpose of operating system is to select one of the processes available in the ready queue for execution. The selection process will be carried out by the CPU scheduler. It selects one of the processes in the memory that are ready for execution. So here, the CPU scheduling occurs based on the ready queue, running state, and awaiting state. The program or the process will only wait once there is a program that are executed in the running state. Okay, so the CPU or the central processing unit will dispatch a process that are available in the ready queue and can be considered now as in a running state or executed. Sometimes also the waiting state is choosing or waiting for the input-output peripheral for the CPU in order to be executed and processed by the use of the operating system. So the basic concept of the CPU scheduling, just like in a single processor system, since the single processor system can only process one program at a time, other must wait until the CPU is free and can be rescheduled. So that is why we have multi-programming to make the process running at all times to maximize the CPU utilization. Several processes are kept in memory at one time when process has to wait the operating system. Takes the CPU away from that process and give the CPU to another process. So this pattern continues. Every time one process has to wait, another process can take over the use of CPU. Scheduling of this kind is a fundamental operating system function. Almost all computer resources are scheduled before use, and the CPU is one of the primary computer resources. Thus, its scheduling is central to operating system design. Here, as you can see, the illustration of the CPU input-output burst. Okay, the CPU burst is when the process of the program, or this is a process of the program by the use of the load, store, add, and read from the file. In waiting for input-output, this is when the CPU needs to wait for input-output peripheral. Okay, and continues. So here in the illustration is the distribution on how the burst time or burst duration in millisecond. So going up, that is when the burst time finishes the process of the program, in high performance and can finish the program. Okay, so here the CPU scheduler classified into two, and that is the non-preemptive and preemptive. Switches from running to waiting state, and also switches from running to ready state. Switches from waiting to ready state and terminates. This is what we consider non-preemptive. And there are some CPU scheduling algorithm that applies non-preemptive. While also, there are some CPU scheduling algorithm that uses preemptive when it is considered the access to share data or used to access the share data, and also consider preemption while in kernel mode, and also consider interrupt occurring during crucial operating system activities. Dispatcher is another important component in CPU scheduling that provides a process with total control over the CPU. Okay, so the dispatcher selects switching context, or also used in switching to user mode, jumping to the proper location in the user program to restart the program. So the dispatcher has its what we call dispatch latency. This is the time it takes for the dispatcher to stop one process and start another running. Okay, so this is what we consider the time for the dispatcher to stop one process and start another running process. In CPU scheduling, we also have the scheduling criteria, and that is the CPU utilization, the throughput or the turnaround time, also the turnaround time, the waiting time, and the response time. But it is divided what particular process are need to maximize and to minimize. So the CPU utilization, the throughput is the scheduling criteria that are need to maximize, while the turnaround time and the waiting time, response time, that is to minimize in CPU scheduling. So when we say CPU utilization, this is what we want for the CPU. Okay, so we want for the CPU to continuous use as possible. So we want the CPU use as many as the process can take over to allocate and execute to provide a specific output. While the throughput in scheduling criteria is a number of processes that complete their execution per time unit. The turnaround time, this is the amount of time to execute a particular process. Also the waiting time that are need to be minimized in scheduling criteria, and that is what we consider the amount of time a process has been waiting in the ready queue. And then the last is the response time. This is the amount of time it takes when the request was submitted until the first response is produced, not output for time-sharing environment. There are different types of CPU scheduling algorithm, and the first one is the first come first serve scheduling or the FCFS. With this scheme, the process that requests the CPU first is allocated the CPU first. So we can refer the FCFS to queue on how the queue provide the process. So this is how the queue used in executing a program, and that is whoever comes first will be the first that are accommodated. So here, the illustration for FCFS provided the burst time and the process, the P1. Okay, the burst time, this is the amount of time finishes the program before it is executed. So the P1 has a 24 millisecond burst time, the P2 3, and also the P3 has also 3 millisecond burst time. So the P2 need to wait for 24 milliseconds before it is allocated in the CPU. Since the P1 requires 24 burst time before it is executed. So by the way, the burst time, it is amount of time finishes the process before it is executed by the CPU. So in adding the total average waiting time from P1, P2, and P3, okay, we will be having 10 millisecond, okay, because the P2 needs 24 second for 24 burst time to wait before it is allocated. Okay, so P1 is 0, P2 is 24, and then the P3 is, it has 3 burst time. So by adding it, divide into 3, we will be having a total of total average waiting time. And it takes a long average waiting time for 3 processes. Okay. Unlike if we will consider to allocate first those with shortest job, okay, so we have P2 and P3. The P2 has only 3 burst time, so we will consider first this is the first program that allocates the CPU. The P2, P3, same with, has a 3 burst time. And finally the P1, since it has 24 burst time. Okay, so we will only have a total average waiting time into 3 milliseconds. Okay, because we considered 6 by adding 3 burst time for P2 and P3. So we have 6 burst time, 0 for P2 since there is no burst time that are need to use before the P2 is being executed. And we have 3 because the P1 needs only to wait for 3 burst time before it is allocated. So a total of 3 milliseconds. What is the advantage and disadvantage of FCFS scheduling? Although it is simple and fair, but the FCFS has to wait. Okay? Waiting time depends on arrival time. Short process stuck waiting for long process to complete. And that is, okay, the disadvantage and advantage of FCFS scheduling algorithm. The next CPU scheduling algorithm is the SJF, or what we considered or what we know or considered the shortest job first scheduling. This algorithm associates with each process the length of the process's new CPU burst. When the CPU is available, it is assigned to the process that has the smallest next CPU burst. The shortest job first scheduling is probably optimal, providing the shortest average waiting time. Okay, consider that we have the process and burst time. The P1, P2, P3, P4 for the process, and burst time. So for the P1, we have 6 burst time, P2, 8, P3, 7, and P4, 3 burst time, millisecond. Okay, P4 has the shortest burst time, so it is the first to be allocated by the CPU. Okay, 0 starts from 0 since there are no available, or since this is considered the first process that are need to be allocated, so 0. So the P1, okay, is the next process that are located after the P4 since it has only 6 burst time. Next is the P3 since it has 7 burst time next to P1, and P2 is the last process that has an 8 burst time. Okay, so the average waiting time is 3 because the P1 needs only to wait for P4, and 16 because because the P2, since this is the process 2, needs only to wait 16 millisecond to be executed. And the P3, 9, because by adding the P4 burst time and the P1, okay, we have 9. And 0 for the P4 because it is considered the shortest job first, okay? It has the shortest job. So that is why it is the one who are allocated first. So divided into 4, we only have 7 milliseconds. As an example, consider the following 4 processes with the length of CPU burst given in millisecond. Okay, so another example is the same process. We have P1 to P4. The arrival time for P1 is 0, P2 1, P3 2, and the P4 is 3. The burst time, okay, for P1 is 8, P2 4, P3 9, and also the P4 is 5. Okay, since the P1 is considered the first program that are need to be executed, it allocated first the CPU, so it start from 0. Okay, on first millisecond, the P2 arrives. Okay, so that is why, as you can see, okay, here in the total average waiting time, 10, since the P1 here, okay, here, 10. Okay, 10 minus 1, since the first millisecond was already allocated by the CPU and terminates because the P2 arrives. Okay, 10 minus 1, and the P2, since the arrival time is 1, so 1 minus 1, okay, here in the equation, 1 minus 1. And next is the P3. So here 17 burst time, okay? The P3 needs to wait 17 milliseconds to be allocated in the CPU. So since the arrival time of the P3 is 2 here, okay? So 17 minus 2, okay, is also in the equation. And 5 minus 3, because the P4 needs only to wait 5 milliseconds. And since its arrival time is 3, okay, 5 minus 3. Okay, so provided 10 minus 1, 1 minus 1, 17 minus 2, and 5 minus 3, the total, adding it, divided into 4, we have 26 divide 4, so we only have 6.5 milliseconds. So this is considered the total average waiting time. Here in shortest job first, okay, the given example is the shortest remaining time first. It is also important part in shortest job first. If a new process arrives with a shorter burst time than remaining of current process, then schedule new process. Okay, so there is a division. Okay, the example given what we have kanina, the P1 allocated in 1 millisecond, then it terminates because the P2 has arrived. So this is what we consider the shortest remaining time first and allocate another process. Further reduces average waiting time and average response time, but it is not practical, okay, because we cannot identify, or we cannot know the future total average waiting time because it allocates another process and then go back again for the first process. Okay, so the same what we have kanina. So the SJF scheduling, its advantage is optimal. Yeah, its minimum average waiting time is very short. The average response time also decreases. But the disadvantage is that it is not practical. It is difficult to predict the burst time. And learning to predict also the future. Okay, so it is not practical to find out the exact burst time in the future or to know the total average waiting time. what we can have overall in the process. And sometimes it also may starve the long jobs. Okay? Another CPU scheduling algorithm is the round-robin scheduling. It is designed specially for time-sharing systems. It is similar to FCFS scheduling, but preemption is added to enable the system to switch between processes. It has similarity with FCFS, but there are also added preemption in the process. So later on, we'll have our example. So a small unit time called a time quantum or time slice is defined. A time quantum generally from 10 to 100 millisecond in length. So here in round-robin scheduling, okay, there is what we call time slice because the time consumed by the first process, okay, can be allocated to other processes. Okay, that's why it is called round-robin scheduling. And then go back again to the first process. So here in the given example, the round-robin scheduling provide three processes, and that is the P1, P2, P3. The burst time is 24 for P1, P2 is 3. The P3 also have 3 burst time or 3 milliseconds. So let us calculate the average waiting time for this schedule. So the P1 waits for 6 milliseconds, 10 minus 4, okay, because on a 4 millisecond, the P2 arrived and it is allocated by the CPU. So the P1 terminates and the P2 allocates the CPU. So that's why 10 minus 4. Here, the P1, we have 10, and since it is allocated by the CPU first, 4. Okay, so in the equation, 10 minus 4, okay, and the P2 allocate after the 4 milliseconds. And the P3 waits for 7 milliseconds because it allocates by the CPU after the P2. Since the P2 has 3 millisecond burst time, so we will add 3 to 4 because P2 waits for 4 milliseconds after it is allocated by the CPU, since the P1 first burst time is 4 milliseconds. Okay, so 10 minus 4 for the P1, P2 waits for 4 milliseconds, and the P3 waits for 7 milliseconds. Okay, so 3 plus 4, we have 7 milliseconds for P3. Thus, the average waiting time for this is 17 divided 3, okay, we have 5.66 millisecond. So after 7 millisecond waited for P3, and then the P3 finishes its burst time into 3 millisecond, and finally the P1, okay, allocate by the CPU. Since first the P1 is allocated, okay, that is why we have 10 minus 4. Okay, then followed by after for the 10 millisecond, okay, it is divided or it is sliced. The time is sliced for the P1. So we have 10, 14, 18, after 14 milliseconds, okay, another 18 millisecond, wait, okay, 22, 26, and 30, okay. So the 24 millisecond burst time for P1 is divided, okay, or it is sliced, okay. The time has sliced in order to provide its processes, okay, and that is why you have here, okay. Okay, so ito yun kanina. Okay, and that is what we call round-robin scheduling. Okay, so instead of to consume the 24 burst time millisecond or 24 millisecond, okay, ang ginawa ni round-robin scheduling, hinati-hati niya ang 24 burst time. So, since the P1 allocates by the CPU after 4 millisecond, okay, that is why we have 10 minus 4, and after that, after the 10 burst time, Okay, hinati-hati niya, okay, until it finishes the total burst time for the P1. And that is what we call round robin scheduling. Okay, there are different classification of the duration of time slice in round robin. So we have short quantum, long quantum, and typically keep between 10 millisecond to 100 millisecond. It depends on the scheduling processes. The advantage of round-robin scheduling, it is fair. Each process gets a fair chance to run on the CPU. It is low average waiting time, and when burst time vary, and faster also in response time. While its disadvantage is it increased context switching. Okay? From also context switches are overheads. Okay? It can probably okay provide a multiple switching in during the process, and it will not be uh, find out or the total average time, or can be considered overheads, or context switches are overheads. Also, high average wait time when burst times have equal length. Another CPU scheduling algorithm is the multi-level queue scheduling. A multi-level queue scheduling algorithm partitions the ready queue into several separate queues. So the ready queue, okay, on the ready process, what can have here in multi-level queue scheduling is it separates into several queues, okay, located on the ready queues. So all the available processes in the ready queue can be separated into a queues, and that is what we call multi-level queue scheduling. Another scheduling algorithm is the multi-level feedback queue scheduling. It allows a process to move between queues. The idea is to separate processes with different CPU burst characteristics. If a process uses too much CPU time, it will be moved to a lower priority queue. Okay, so here in multi-level feedback queue scheduling, when the process uses the CPU and it consumes a large number of time for the CPU, it will be moved to a lower priority queue. And that is what we call multi-level feedback queue scheduling. We also have thread scheduling. So keeps track of the load on every CPU in the system, migrating thread from heavily loaded CPU to lightly ones. So when we say thread, this is, I think, multi-tasking or multi-processes. So what we can have here in thread scheduling is it migrates the thread from heavily loaded, okay, when the CPU, when the thread scheduling find out that the CPU encounters a heavy loaded program or processes, it will now use to make it or to migrate, okay, to light, okay, to light load, okay, and that is the responsibility of the thread scheduling. So it keeps track of the load on every CPU system. If it finally find out, it migrate the load to other, okay, to other, or it migrate from heavily loaded CPU to lightly ones. And I think it is used in multiple processor or multi-processor system. It cannot be done in single processor system because a single processor system can only process one process at a time. Okay, so we can only use thread scheduling in multi-processor system. So the multiple processor scheduling or multi-processor scheduling focuses on designing the system scheduling function, which consists of one or more than one processor. It is different to single processor system since the single processor system can do process at once, but here in multiple processor scheduling can do more than one processor. So in general, multi-processor scheduling is complex as compared to single processor scheduling. The multiple CPUs in the system are in close communication, which shares a common bus, memory, and other peripheral devices. And that is why multiprocessor scheduling is complex, because it shares a common bus, memory, and other peripheral devices, which is very difficult to okay to identify, okay, and which is difficult to know and configure its processes. And that is how the multiprocessor scheduling is complicated. Another CPU scheduling algorithm is the real-time CPU scheduling. It is classified into two, and that is the soft real-time system and the hard real-time system. The soft real-time system, there are no guarantee as to when critical real-time process will be scheduled. So we don't have identification of what time, what critical real-time the process will be scheduled, and it is difficult for real-time CPU scheduling to know the process or to provide scheduling for the process. While the hard real-time system, task must be serviced by its deadline. Okay, so there is a specific time for the hard real-time system to conduct processes or scheduling for every program. Okay, there is a exact time, okay, for the program to be executed and allocated, and that is what we call hard real-time system. Next is the operating system example. We have the Linux scheduling, Windows scheduling, and Solaris scheduling. This is located in operating systems, okay, aside from what we have mentioned earlier. So Linux scheduling and Windows scheduling, and also Solaris scheduling. Okay, the difference I think of the Linux scheduling and Windows scheduling is that the Windows is located, or what we have, okay, two different personal computers nowadays. And Linux can be used, I think, for a complex program. And then the Solaris scheduling is used in Oracle, okay, Oracle operating system, and that is what we call Solaris scheduling. In evaluating the algorithm evaluation uses analytic evaluation, okay, uses different evaluation method to find out what are the best scheduling algorithm. So based on the given example earlier, the algorithm evaluation is the one who evaluates what is the best algorithm that can be applied to different processor system. Okay, it might be in the single processor or in the multi-processor. So one major class of evaluation method is analytic evaluation. It uses the given algorithm and the system overload to produce a formula or number to evaluate the performance of the algorithm for the workload. Deterministic modeling is used in algorithm evaluation. It is one of the type of analytic evaluation. This method takes a particular predetermined workload and define the performance of each algorithm for that workload. So what is the use of deterministic modeling? This is used to identify the performance and the workload of each algorithm. Okay, so here, for example, assume that we have the workload shown below. All 5 processes arrived. Okay, the P1, P2, P3, P4, and P5, and also the corresponding burst time. So the P1 has 10 burst time, the P2 is 29 burst time or millisecond. The P3 has 3 burst time. The P4 has 7 and the P5 has 12 burst time. So if we will consider the FC, FS, the SJF, and the RR scheduling algorithm for this set of processes, which algorithm would give the minimum average waiting time? So for the FCFS algorithm, we would execute the processes as, since the P1 is considered the first, okay, the first job that need to be allocated by the CPU. So the P1 has 10 burst time, okay, before it is executed. So the P2 needs to wait for 10 milliseconds before it is allocated by the CPU. Okay, so since the P2 has 29 burst time, so the P3 needs to wait for 39 burst time because 10 plus 29 is 39 burst time. Okay, start from P1 to P2. And then followed by the P4, so the P4 needs to wait for 42 burst time by adding the 3 burst time of P1, P2, and P3. Also, the P5 has need to wait for 49 milliseconds because the total average waiting time for the P1, P2, P3, and P4. So in order to get the total average waiting time, so we have 0 since the P1 is the starting point to be allocated, or there's no burst time for the P1 to wait. So we have 0 plus 10 plus 39 and plus 42 plus 49 divided into 5. It takes 29, it takes 28 millisecond or total average waiting time for the FCFS scheduling algorithm. Whereas, if we will be using a non-preemptive SJF scheduling, we execute the processes as first is the P3 since it has the shortest burst time. So 3. After the 3 millisecond, the P4 is allocated. So the P4 needs only to wait 3 millisecond after it is allocated by the CPU, followed by the P1, next after by the P4, the P5, and also the P2. Okay, since the SJF follows the rule of allocating those job that has its smaller processes, a smaller burst time. Okay, so to get the total average waiting time for the processes, we only have 13 millisecond compared to FCFS, which has 28 milliseconds. Okay, next, if we will now be using the RR algorithm compared to FCFS and SJF. Okay, so this is the process as follow. Okay, since the round robin, follow the time slice or the time quantum, the burst time uses the burst time but can also be sliced. So pwedeng hati-hatiin ang oras, ng isang process as long as, if other process is allocated. But the process, needs to finish the total average burst time, for every processes. So here, the P1 is the first allocated by the CPU, which is, 0. Followed by the P2. The P2 allocates the CPU after 10 burst time. Then followed by the P3, we have 20. After the 20 burst time by the P2, the P3 is allocated. And also the P4, we have, so 23 burst time. The P4 needs to wait for 24 burst time before it is allocated. The P5 and followed, and next again the P2. So the P2, even though it is the second allocated by the CPU after by the P1, so since the P2 has a large burst time, it is divided into 3. So the P2 burst time waited for P1 finishes in 10 burst time, and after the P5, the P2 allocate again by the CPU, and after 50 millisecond, okay, the P5 arrives and it is the next allocated by the CPU. So after 52 millisecond, the P2 allocates again by the CPU, and that is what we consider round robin scheduling. Okay, so to get the total average waiting time, so 0 plus 32 plus 20 plus 23 plus 40 in divided by 5, we have 23 millisecond. Okay, so in round robin, the waiting time is 0 millisecond for process P1, 32 millisecond for process P2, 20 millisecond for process P3, and 23 millisecond for process P4. And also the P5 has 40 milliseconds. Okay, but as you can see in the given example, okay, there are times that the process allocated next and uses another time, okay, then allocates again by the CPU. And that is what we call round robin scheduling. So the total average waiting time is 23 milliseconds. So in contrast or comparing to other processes or other algorithm to SJF and FCFS, okay, only the SJF has a minimum total average waiting time, and that is 13 millisecond compared to FCFS and round robin scheduling. We can see that in this case, the average waiting time obtained with the SJF policy is less than half that obtained with FCFS scheduling. The RR algorithm give us an intermediate value. So, indeterministic modeling is simple and fast. That's why we already identified those scheduling algorithm that has a limited or minimum total average waiting time. However, it requires exact number for input and its answers apply only to those cases. Okay? So that is what we use deterministic modeling in different CPU scheduling algorithms. Simulation, to get more accurate evaluation of scheduling algorithm, usually the simulations were used. Running a simulation involves programming a model of the computer system. Software data structures represent the major components of the system. So after evaluating, we can now use the simulation process. And finally, the implementation. Even a simulation is of limited accuracy. The only completely accurate way to evaluate a scheduling algorithm is to code it up, to put in the operating system, and see how it works. So this approach puts the actual algorithm in the real system for evaluation under the real operating system conditions. CPU scheduling is the task of selecting a waiting process from the ready queue and allocating the CPU to it. The CPU is allocated to the selected process by the dispatcher. So programmers have the options what best CPU algorithm suitable for FCFS, SJF, SRTF, and RR scheduling. Okay, and I think that's all for my presentation. Thank you and God bless everyone.